So hello everyone, Foundations of Language Technology, lecture number 13. We're dealing with semantics today. As you recall from our course overview, we're now at the very top of our diagram. That means we're at the very top of the analysis that we're conducting in this course. And this analysis today deals with the meaning of words and sentences. And we do so using this paradigm of deep learning, which is also known by the name of artificial neural networks, and which is inspired by the working of the human brain. So what are word vectors, also known as word embeddings? Simply spoken, word vectors, word embeddings, are vectors associated with words from the dictionary. So we have our dictionary, let's say all of the English words in the English language. Associated with each word is a vector. This vector is a sequence of numbers, just like on a formal manner. However, then when we visualize those vectors, and we can do so, for example, using dimensionality reduction, because human cognitive perception is limited to 2 or 3 dimensions. So when we then visualize those vectors, we find a very interesting property, namely that similar words are represented close by in the vector space. And this means those word vectors, those word embeddings, actually capture meaning, they capture semantics. And this is a wonderful property that has been leveraged in the last 10 to 15 years in the NLP community. Now the question is, how do we know that these vectors capture semantics? And to understand why they do capture semantics, we need to understand how those vectors have been derived. Simply speaking, those vectors capture semantics because they have been trained to predict contexts, and context is one definition of semantics. So there's an old definition from the 1950s that says, you shall know a word by the company it keeps. And this means if you know the surroundings of a word, if you know the context of a word, you also know its meaning and you also know its semantics. And because those vectors, or those models that output vectors, are predicting context and are modeling context, then intuitively the resulting vectors should also represent semantics. Now, so to illustrate, to give an illustration and an example of why the meaning of a word is stored in its context, let's look at an example case here. Let's assume there's the word wampimuk, which all of us may not have heard of before. So we hear a sentence like, he filled the wampimuk, passed it round, and we all drank some. Now, even though we may not know what the word wampimuk actually means, from this context, we can infer that maybe it has to do something with glass, bottle, or something similar. In contrast, when we hear the same word in a different context, such as, we found a little hairy wampimuk sleeping behind a tree, we would immediately infer, just from the context of this word, that maybe this word is certainly an animate object. So it could be, for example, a little animal, a little animal. So this is the distributional hypothesis that I have already pointed out. You shall know a word by the company it keeps. If you know the context, you know the meaning of the word. And this idea is implemented in the famous word-to-vec model which has been popularized by Tomasz Mikolov and his colleagues in 2013. What they do is they implement the distributional hypothesis in one of 2 ways. So they have the SIBO model, where given a context, one predicts a missing word. So basically one would have the context, same procedure, slot every year, and would have to fill in the missing word. As long slot you sing, please stay slot you are. So here the task is to predict the missing context, or the skip-gram model, where the operation is vice versa, and in a manner that seemingly is more difficult for humans. We only have the center word and we aim to predict the context. Now, those two models are illustrated here, the SIBO model on the left, the skip-tram model on the right. And even though the skip-tram model is less intuitive for humans, I will focus on this in the following description. So for the skip-tram model, we have the center word, and we feed the center word is represented as a one-hot, is initially represented as a one-hot vector. So it means that there's exactly one, and all the other entries in the vectors are 0. Then this center word, this one-hot encoding, is fed into a hidden layer, which is here called the projection layer. And from this projection layer, then is supposed to be predicted the context words. So you see that this is a neural network that has as input one-hot vectors, and as output, it also has one-hot vectors, namely the context words. So the one-hot vectors are the inputs and the outputs. For example, we have the word cat that could be represented by this one-hot vector, or the love, which could be represented by a different one-hot vector. And of course, the size of these vectors is the size of the vocabulary. So if we have 1 million words in the English language, the size of these vectors would be 1 million. So here in the middle, so we train our model on this task, but after the training has finished, we're only interested in this matrix E here, which is also the embedding matrix. What is stored in this embedding matrix later on is the word embeddings, or the word vectors. And how do we get the word vector for the nth word? Let's look at the 4th word in the vocabulary, for example, which would be stored as a 4-hot vector. We have our embedding matrix here. Now, the size of this embedding matrix is the same size of this 1-hot vector. And so it has actually, well, being a matrix, it has 2 dimensions. The one dimension is the dimension of the rows. So how many rows does it have? It has exactly as many rows as there are in the vocabulary. So if the English vocabulary has 1 million words, it will have length 1 million, and this is the same size as the 1-hot vector. And in the row dimension, so to speak, it has d dimensions, and d is a number that we can set. So this is actually the word vector. So this is the dimensionality of the word vector. Now, if we multiply a 1-hot vector with a matrix in this manner, what we get out is the nth or the kth row. In this case, it's going to be the 4th row. So we're going to get out the fourth row of this matrix, and this is going to be the embedding of the 4th word. After training is finished, we only care about this matrix E. We multiply a word's 1-hot vector with E to get the embedding of this word. Now, what are the properties of the embeddings? And this is now empirical. So we have set up an optimization problem which intuitively makes sense. Intuitively, it should train vectors that have this property that similar words have similar representations. But now we look into the outcome, if the outcome actually satisfies what we hope it would satisfy from the training objective. And empirically, we observed the first property, namely that semantically similar words are nearby in the vector space. Secondly, we also observed that syntactic or morphological properties are sometimes also preserved in this vector space, very interesting. And we look into those empirical observations. Let's say here is a vector space of many words. And if we would look into those words, we could, for example, see, let's say, words like charger, battery, Bosch, drill, which we all perceive of being semantically similar, are close by in this vector space here. And again, this is a 2-dimensional reduction. Similarly, we would find that words like kitchen, sink, bathroom, toilet, which also we perceive of as being semantically similar, are close by in the vector space. And we could observe many examples and indeed find that in many cases, semantics is well preserved in those vector spaces that are derived from this embedding matrix. We also see the properties of syntax or morphology. Let's look, for example, at verb tense. We find that words like walking and walked which are different morphological variants of the same word. They have a similar distance to each other as the word swimming and swam. And there are many cases where this is actually preserved. So the morphological difference between two words is preserved in the vector space. We also see this when, for example, we look at cases like male-female, where king and queen have the same distance to each other than men and women. Or we have many cases of like a country and its capital. They stand in a similar distance and a similar geographical distance to each other and a geographical relation to each other in the vector space as many different other instances of countries and capitals such as Italy and Rome, Germany and Berlin. Now those vectors, those embeddings have been so popular, which was the reason that there was a very big research initiatives on them, which meant that many different mutations, variants have resulted as a consequence. And that's probably with everything that is spreading, that you can see many different variations and mutations coming out. So what we have seen for embeddings, we have seen that embeddings that are more syntactically oriented, where the semantic component is not so strong. We've seen embeddings that employ character level information. So far, those embeddings do not exploit any character level information. If two words have many characters shared, such as walking and walked, the models do not specifically exploit this fact. But if you design character level model, such as the fast text model, then you can exploit such fact. And in such models, they have an easier way, or they have an easier they find it easier to deal with spelling variations, typos, and languages that have rich morphology, much richer than English, where there are different variants of words, let's say German, Latin, or Czech. Finally, another very fruitful avenue of research are the bi- and multilingual embeddings, where words from different languages, from two or more different languages, are stored in the same vector space. Finally, the most important and the most recent innovation are the so-called contextualized embeddings, which have a very they encode a very obvious property, but this property has been missing from the previous embeddings as word-to-vec, which nowadays are called static embeddings. And we're going to talk about the last two embedding variants in the next slides. So the bi- and multilingual embeddings are very interesting in the sense that they store words from different languages in one and the same vector space, so that not only words that are monolingually similar to each other, such as eat and drink or bike and car, are close by in vector space, but also the correspondences in different languages. So in such spaces, we would see that eat and essen and drink and trinken are close by in the vector space because they represent concepts that are similar across two languages. Now, the contextualized embeddings, what they have as a core contribution is that each word is assigned a different embedding depending on its surrounding context. And they use language models to do so. For example, let's look at a word like the word can. The word can in different contexts may mean different things. In the first sentence here, I can see you, it's a verb and it has, it's a modal verb and it expresses an ability to see someone else. In the second sentence, please give me that can, it represents something very different. It represents a noun, certain noun that is used as a placeholder to put something inside. So this word has very different meanings, at least two different meanings. It's ambiguous, it's polysemous, and that is the case for many languages, for many words in any language, because language has this property to be ambiguous and to be polysemous, as we have repeatedly stressed throughout discourse. And of course, The classic static embeddings cannot distinguish between those two occurrences because they would always assign the word can the same embedding. So we really need to have models that can represent words differently in different contexts. And those models have become very popular after 2018, and they have funny names such as Elmo and BERT. But this is just a funny side aspect of them. And they have almost completely replaced the previous static embeddings. And why have they? Because they have been extremely successful. So the models that use contextualized embeddings are much, much better than models that use static embeddings. Good. So let's again illustrate how Elmo and BERT, the first two most popular models. Nowadays, BERT is the most popular model and variants of BERT are the most popular models, but let's see how they do it. So BERT does contextualized representations, computes contextualized representations. And the cool thing about BERT is not only contextualized representations, but it has been pre-trained. So there's this concept of pre-training that goes along with BERT especially. And this pre-training means that the model has been pre-trained on huge amounts of data. So it has seen a lot of English language text, and therefore it can induce very good representations. And again, here on the right, we see this distinction or this usefulness of contextualized representations for the mouse, for the word mouse, where we see that depending on the context, the word mouse may have different representations, and they may even be orthogonal to each other. For example, in the case of the computer mouse or the case of the animate mouse. Now, how does BERT work during the training? We see here that BERT is such a very deep architecture. It has 12 or 24 layers, but basically it's a neural network that is just a deep neural network. It uses a particular network architecture, which is called a transformer, which we're not going into in this lecture. What is it doing during pre-training? During pre-training, it's doing masked language modeling. So what it's basically doing, it's hiding out certain words in the input, and it tries to predict those missing words. In a sense, this is similar to what word2vec has been doing. Some words are missing, and BERT tries to predict those words. And what turns out to be the case is that if BERT is pre-trained with such an objective, then it acquires a good understanding of any language on which it has been trained, English, German, French, whatever you have. So it really begins to understand the language, and it induces representations that capture meaning. So once BERT has been pre-trained, you fine-tune it on a small data set of your choice. For example, if you do part of speech tagging or named entity recognition, you would use such a small label data set to just fine-tune BERT. So basically it has already its basic structure, but you adjust it a little bit. And what comes out is that BERT will perform very well on this data. Now that we have seen, the question is, how do we know the vector captures semantic? We go to the next question, namely, how do we compare the semantic similarity of two words if we have gotten contextualized or static representation? And this is a question that we're not going into very much, so we will not cover this at depth, or we just give a simple practical answer. We take the word vectors, let's say the static word vectors, and we compare them using cosine similarity. And why are we using cosine similarity? Well, because it's the most popular measure, and there may be reasons why it's popular. We could also use the vector distances, but the cosine similarity has turned out to be the most popular measure in the NLP community to compare two vectors. So basically what the cosine similarity is doing is, let's assume we have a high dimensional vector. In the two-dimensional case, we can draw those vectors. In a plane, and here are two vectors drawn. You see this could, for example, be the vector 3, 2, and then we draw it like this. This could be the vector 2, 3. And then the cosine similarity is measuring the angle between the two vectors. And if this angle is very low, the vectors are supposed to be very similar. So those vectors are very similar. Those are orthogonal vectors which stand orthogonal to each other. So their similarity would actually be 0. because they point into different directions of the space. And if they point into opposite directions, so if one vector goes in this direction and the other one points in the completely opposite direction, they would have a cosine similarity of -1, or at least negative. Now, this is now how we compare two vectors. A third question that we have is, how do we evaluate the quality of our word embeddings or our word vector? So what the community has been doing is they use benchmarks such as the popular word similarity 353 dataset and compare the similarities that humans have assigned. So in this word similarity 353, we have many different word pairs that have been labeled by human annotators. And we can also compute the similarity of the word embeddings by doing the cosine similarity, for example. So we have any two words, we have their vectors, we compute the cosine similarity between the word vectors, which says how similar are these two words, right? First, we say how similar are these two vectors, but then we take that to mean how similar are the two words. And then we compare this number that has been produced by our algorithmic technique to the number that has been assigned by humans. So this is an excerpt of the data set as it looks. So as you see, we have word pairs such as plane and car, train and car, telephone and communication. And here we have the similarity, and this is an average similarity of, let's say, 10 human annotators that have said plane and car are similar at a level of about 5.77 versus train and car a little bit more similar, and words that are less similar, for example, smart and student. So the scale is 1 to 10, for example, where 1 means not very similar, not similar at all, and 10 means completely synonymous, for example. So again, as I said, we can compare those numbers that are assigned to humans to numbers that are the result of comparing those vectors, for example, using cosine similarity. And then we can correlate the numbers that the that the embeddings give to the numbers that the humans have given. And if this correlation is very high, we say that our embeddings are of high quality. Good. Now we have seen how words can obtain embeddings. Let's also see how sentences can obtain embeddings. So word embeddings are vector representations of words, but in natural language, we are often very much interested in the meaning of whole sentences. So not only individual words, but complete sentences. And that could look like the following. We assign, so we have 3 sentences here. Lion is the king of the jungle. The tiger hunts in the forest. Everybody loves New York. So those are 3 different sentences. And we assign those 3 different sentences, each 1 vector, right? And then we compare how similar actually is lion is the king of the jungle to the tiger hunts in the forest, and how similar is it to everybody loves New York. Well, intuitively, we would say those two are more similar, and that's also what we see in those vectors. Like the angle is smaller here than it is compared than it is between those other 2 vectors. Now, how can we induce sentence embedding? So one of the simplest ways is if we have a sentence of 10 words, we can get the embedding for each of the 10 words, and we simply average those 10 embeddings. And it turns out empirically, even though this is theoretically not a very good idea because it discards all the order of the words. So a sentence like man bites dog and dog bites man would have the same representations, even though they mean things that are definitely different. So even though in principle that is not the best of ideas, in practice it works surprisingly well. There is also some easy to use software which is based on BERT. So it basically just averages BERT embeddings. So it averages contextualized embeddings, which is smarter than averaging word embeddings because the order of word is somehow preserved. And this easy to use and nice to use software is called SBERT, and it's given at this link here. Now, how do we evaluate sentence embeddings? We do it in the same way as for word embeddings. We use a human benchmark for comparison. For example, the STS benchmark. STS stands for Semantic Textual Similarity. And in this benchmark, what we do have, we have different sentences, such as girl is styling her hair and a girl is brushing her hair. And again, we have human annotators that annotate the similarity of those sentences on a scale from 1 to 5, where typically 1 would be low similarity and let's say 5 would be high similarity. Even though it's a little bit surprising that styling and brushing is considered to be so dissimilar here, let's look at another example. One woman is measuring another woman's ankle. A woman measures another woman's ankle, and we see, okay, those two are almost perfectly similar. So we have a score of 5.0. And again, what we would do here is we would compare those human assigned similarity scores to automatic similarity scores induced by comparing the distance or the similarity between two sentence embeddings. Good, so this is already finishing our today's lecture. We have seen semantics from embeddings. We have seen embeddings are vector representations for words or for sentences. We have seen that similar words and similar sentences may have similar representations if the embeddings are induced, for example, based on word2vec or BERT, which in some way implement a hypothesis, namely the distributional hypothesis, that a word, the meaning of a word or the meaning of a sentence can be inferred from its context. And those embeddings are very easy to use in applications. They are very good features. But if you have sentence embeddings, you can feed them directly into your neural net, or you can use BERT, which by itself, you don't need to feed in anything inside. It's both an embedding and a complete architecture, but it's also very easy to use in practice. Good, with this, I thank you and see you later.